Before I really get into the new information, I did want to just bring up this one piece. Yesterday in lab, I introduced the concept of enthalpy. Enthalpy is it's referred to as the enthalpy of reaction, and sometimes it's referred to as the heat of reaction. The reason for that is because if you'll recall, when we're dealing with constant pressure systems, which many of our chemical reactions take place in, when you're dealing with a constant pressure system, the enthalpy, the change in enthalpy is equal to the Q, which is heat. So that's why it's often referred to as heat of reaction. Enthalpy is very similar to energy. They don't differ drastically unless you have a lot of gas molecules, in which case they will differ drastically. But in general, the enthalpy is a good indication of the energy of the system. Now, with respect to enthalpy, enthalpy is represented with a capital H. It is a state function. It means that it doesn't matter how you go from reactants to products. All that actually matters is what is the identity of the reactants and what is the identity of the product. A favorable process will be one in which the enthalpy is exothermic, meaning heat exits the reaction. Because it is exiting the reaction, it means that the system is losing that energy, and so our sign notation is a negative value. An unfavorable process is one that's going to require an external influence in order to occur. Unfavorable processes with respect to enthalpy are endothermic processes. Endothermic processes mean that the energy enters the system, just like reactants enter the system. Because energy is entering the system, it means that the system's energy is increasing. And since the system's energy is increasing, we are dealing with a positive delta H. So this is just a reminder of enthalpy. And the reason I wanted to remind you of enthalpy is because the rest of our conversation is all about enthalpy. When we start looking at Hess's law, we're going to be dealing with the enthalpy of reaction. When we look at bond energies, we're going to talk about estimating the enthalpy of reaction. When we look at enthalpies of formation, we're going to be talking about determining the enthalpy of reaction. So the rest of the conversation in this chapter is all about enthalpy. Okay, so what we're moving into now is relationships involving enthalpy. When we look at a chemical reaction, there is an energy associated with that chemical reaction. Now, there are three relationships that we can just talk about with respect to the enthalpy of a reaction. The first is going to be what occurs when you multiply a reaction by some factor. In other words, you're multiplying the coefficients of the reaction by a factor. Let's just look at a generic example. Let's say I have the reaction of A plus 2B goes to form C plus 3D. And this reaction has a delta H equal to 155 kilojoules. Now, according to this relationship that I just described, if we say, okay, instead of 1A, we're going to have 3A plus 6B going to form 3C plus 9D. The question is, what is the delta H for this reaction? Well, if you'll recall yesterday, we can talk about stoichiometric amounts. We did some mathematics associated with the stoichiometric amounts. Well, with this relationship, what we realize is that going from this first equation to the second equation, we multiplied the entire thing by 3. You will do the exact same thing to the enthalpy. You will multiply it by 3. Therefore, the delta H for this second reaction is going to be 465 kilojoules. So again, the first relationship we're talking about is if you multiply the coefficients of a balanced chemical reaction by some variable, you do the exact same thing to the enthalpy. And that is because the enthalpy is related to the reaction stoichiometrically. Now, the second relationship is the reversing of a chemical reaction. When a chemical reaction is reversed, you simply change the sign of the chemical reaction. So let's go back to the original equation of A plus 2B goes to form C plus 3D. If I reverse this reaction, where it's C plus 3D goes to form A plus 2B, then what would happen is if the original delta H is 155 kilojoules, then this reverse reaction would be a negative 155 kilojoules. So in other words, you reverse the reaction, you change the sign. Now, what happens when you do multiple functions on the same reaction? You can do multiple functions on the same reaction, and you're going to just do multiple processes on the enthalpy of the reaction. Here I have 2A plus B goes to form C with an enthalpy of reaction of 122 joules. Let me blow that up a little so you can see better. I want to know the enthalpy of the reaction for 2C goes to form 4A plus 2B. What I notice is that in going from the first reaction to the second reaction, I have reversed the process. That means I'm going to change the sign. And the other thing I noticed is that I also multiplied it by 2. So 2C going to form 4A plus 2B is going to have a delta H of reaction that is going to equal a negative 122 joules times 2. The negative is there because I reversed the sign, and the 2 is, we're multiplying by 2 because we multiplied the reaction by 2. Therefore, the delta H of reaction for this process is a negative 244 joules. These relationships where if you multiply the coefficients by some factor, you multiply the enthalpy by that same factor. And the second relationship, if you reverse the reaction, you change the sign. All of that is going into our third relationship, which is known as Hess's law. Hess's law states if a chemical equation can be expressed as the sum of a series of steps, then the enthalpy for the overall equation is the sum of the heats of reactions for each step. The chemical equation can be expressed as the sum of a series of steps, then the enthalpy of reaction for the overall equation is the sum of the heat of reactions for each step. And we are going to do a couple of problems associated with Hess's law so that you can see how to apply all of these relationships. The multiplying by a factor, the reversing of a reaction, and Hess's law. We're going to do some problems so that you can see how you apply these relationships to Hess's law. Okay. So here I have carbon solid plus oxygen gas going to form carbon dioxide. It has an enthalpy of reaction of a negative 393.5 kilojoules. I have 2 carbon monoxide gas plus oxygen gas going to form 2 carbon dioxide gas with an enthalpy of a negative 566 kilojoules. And I have 2 hydrogen gas plus oxygen gas going to form 2 water gas with an enthalpy of a negative 483.6 kilojoules. We have been asked what is the enthalpy of the reaction where carbon solid reacts with 1 water gas to form 1 carbon monoxide gas and 1 hydrogen gas. Okay. The easiest way to do this is to use your target reaction. I start with carbon solid. So I'm going to find a reaction that contains carbon solid. And that is going to be the first reaction. My carbon solid is a reactant in the target equation, and it is a reactant in the given equation. Because of that, I'm going to use the reaction and the enthalpy as is. And I'm going to have to flip back and forth, so I apologize. So carbon solid plus oxygen gas goes to carbon dioxide gas. Well, Maybe I won't. Okay. The next one is going to have water gas. Ah. I'm going to look for an equation that has water gas. That is my third equation. I need water gas as a reactant. It is currently as a product. So I'm going to have to flip this reaction or reverse this reaction. The other thing I notice is that I only need one water, whereas in this reaction I have two waters. Well, to get rid of two, I would multiply the entire equation by 1/2. So therefore, I'm going to multiply the enthalpy by 1/2. So I flip the equation and we have H2O gas goes to form H2 gas plus 1/2 O2 gas. And that is going to have an enthalpy of a positive 241.8 kilojoules. Continuing on, the next thing I need is I need carbon monoxide gas. I need carbon monoxide gas, so I look for something that has carbon monoxide gas, and that is the second equation. I need carbon monoxide gas as a product, but it is currently a reactant. So I am going to flip this enthalpy. The second thing I notice is that I have one carbon monoxide gas, whereas in the original equation, I have two carbon monoxide gases. So again, I'm going to have to multiply that reaction by 1/2 in order to get it down to just a single carbon monoxide gas. So we have carbon dioxide gas goes to form carbon monoxide gas plus 1/2 oxygen gas. And that is going to have an enthalpy of a positive 283 kilojoules. Now I'm going to use Hess's law. First, let's get the equation. So basically what you're going to do is you're going to start to combine the things on the left-hand side. So I see I have carbon solid, plus I have an oxygen gas, plus I have a CO2 gas, plus I have a water gas. And we're going to work with the product side. On the product side, I have a CO2 gas. I have a CO gas. I have an O2 gas because 1/2 plus 1/2 is equal to 1. and I have an H2 gas. Now, if it appears on the reactant side and it appears on the product side, just like when we were doing spectator ions, it means it's going to cancel out. So the oxygen gas cancels out, as does the carbon dioxide gas. And so what is left is carbon solid plus H2O gas goes to form carbon monoxide gas plus H2 gas. Since those three equations added up to the target equation, that means that I can add up my enthalpies to get the enthalpy of the equation. And the enthalpy of the equation comes out to be a positive 131.3 kilojoules. Yes. So what I did is you have to look at the left. So I started by looking at the left-hand side of the arrow. There's a carbon solid, there was an oxygen gas, there was a carbon dioxide gas, and there was a water gas on the left-hand side. On the right-hand side of the arrows, there was a carbon dioxide gas, there was a carbon monoxide gas, there was 1/2 oxygen here and 1/2 oxygen there, which made a full oxygen gas and a hydrogen gas. So I then canceled out the things that appeared on both sides, and it was left with the target equation. Did that answer your question? Yeah. And then I used Hess's law, and basically you add up these enthalpies to get the enthalpy of the reaction. Yes.
How did you decide that you didn't need to pursue the hydrogen gas on the left-hand side? Then you did the first three, but then decided you didn't have to come up with another equation.
So when you've used these equations, first of all, with Hess's law, you will be able to come up with the target equation from the three equations given. Now, how we get to these three equations is another story, but you will be able to come up with the target equations of the ones given. So once I had gone through the three equations, I'm not going to use them but one time. And so the hydrogen just, I knew the hydrogen should just fall out because I had used all three equations already.
So as we as beginners, we know that it just falls out.
At this point now, yes. Basically, once you've used all of the equations given, anything that you have not assigned it should just fall out when you do it. The other thing I will say is when I'm working with target equations, let's say this had been oxygen. Because I had two equations with oxygen in it, I would have ignored the oxygen to begin with. Because if you try to make the oxygens work, it's going to get confusing. So actually, all three equations had oxygen in them. So when you have multiple equations with the same substance, ignore that substance and move on to the next substance in the equation. So if I've had oxygen here I would have moved on to the next substance in the equation rather than deal with the oxygen because it appeared in all three equations. Let's look at another example. No. Okay. Let's look at this example. Okay, so again, I'm given a series of reactions and I'm asked for the enthalpy of reaction for a target equation. That is your cue that you're using Hess's law. I start out with carbon. I only have one source of carbon here, and that is going to be in this second equation. Carbon is a reactant, and it is a reactant in that second equation. But I need 3 carbons, so I'm going to have to multiply this equation by 3. Whatever you do to the equation, you do it to its enthalpy. So that would be 3 carbon solid plus 3 oxygen gas goes to form 3 carbon dioxide gas. With an enthalpy of a negative 1180.5. Yes.
Also in the other one, then why do we need to do that?
Carbon isn't in the other one by itself. There's only one equation that contains just C solid. Okay. Then I move on to the next one in line, which is hydrogen gas. I look for the source of hydrogen gas and I see only one source, which is good. That is the second or the third equation. I need the hydrogen gas as a reactant. That is fine. It is a reactant. But I need 4 hydrogen gases, not 2. Therefore, I need to multiply this equation by 2. So we have 4 hydrogen gas plus 2 oxygen gas goes to form 4 water gas. And whatever you do to the reaction, you do to the enthalpy. So I need to multiply the enthalpy by 2. And you get a negative 967.2 kilojoules. Next, I'm going to go to propane. And that will be my top equation that has propane. In the target equation, propane is a product. In the equation given, it is a reactant. So I'm going to have to flip this equation. So that's 3 CO2 gas plus 4 H2O gas goes to form C3H8 gas plus 5 O2 gas. And that has a value of 2043 kilojoules. And it is positive. Now we combine the reactions and we should get our target equation. If you combine the reactions and you don't get your target equation, you know you've done something wrong. So this is a check to make sure you've done it correct. So I'm going with everything on the left-hand side. I have 3 CO2s. I have 3 CO2 gas. I have 4 water gas. I have 3 carbon solid. I have 5 oxygen gas. And I have 4 H2 gas. Going to make the product, I have C3H8 gas plus 5 O2 gas plus 3 CO2 gas plus 4 water gas. Looking at it, the 4 waters cancel because you have 4 waters on the reactant side and you have 4 waters on the product side. The 5 oxygens cancel because you have 5 oxygens on the reactant side and you have 5 oxygens on the product side. And the CO2 cancels because you had 3 CO2s on the reactant side and you have 3 CO2s on the product side. So what is left on the reactant side is 3 carbon solid plus 4 hydrogen gas going to make C3H8 gas. Because the equations added up to the target equation, that means that I will add these enthalpies together. And this has an enthalpy of reaction of a negative 104.7 kilojoules. Which means it is favorable, which means it is exothermic, which means propane does readily form from its elements. Yes.
It's like a CO2 in the equation. Then what do we not have? C? I think we skip the C because there's obviously CO2.
Okay, so I think what you're asking. What you have to look for is exactly what is there. If it would have had CO2, then I would have looked for CO2. And I would have found multiple sources of CO2. So you have to look for exactly what it is asking for. So carbon solid, you need just carbon solid, not carbon in anything. You need just the element. Whereas here, we had propane, so I looked for propane. You're looking exactly for what, and it states of matter also are important. I had to find propane gas, not just propane. If I'd have found propane liquid, then I could not have used this series of equations to get this reaction, because you have to have exactly what it says in the target. Did that answer your question? Other questions?
There'd be a question where you give us like, you don't give us enough information, or you give us the wrong information.
No. You'll be, I mean, it'll be, I'm not that tricky.
So.
I'm not that tricky. It'll be a solve. You'll have to solve for something. Now, you may only have 2 equations instead of 3. The 2 examples I gave you had 3, but you can have 2 equations, you can have 4 equations, you can have multiple equations. The process is the same. Do a step-by-step analysis and make them match. Questions? Okay. Then we're going to move on to bond energies. Previously. Well, first of all, bond energies allow us to estimate the enthalpy of a reaction. Why would we want to estimate the enthalpy of reaction? Well, I don't want to walk into a laboratory and blow something up unless it's easily manageable. So it's better to do a little bit of math up front to try to make sure that when you walk into the laboratory, you don't blow yourself up. So bond enthalpies are another way where we can estimate the energy of a reaction. Now, and that's something to recall. Why can we use bond energies? Well, we go back to the term chemical energy. If you'll recall, chemical energy is the potential energy associated with the relative position of electrons in the atomic nuclei. In other words, the chemical energy is in the bonds. All the chemical energy is in the bonds. And when you start a reaction, you have potential energy. When you end the reaction, you have potential energy. If you'll remember the diagram I gave you yesterday. All of the energy is in the bonds. So that's why we can use bond enthalpies. Now, you've already been introduced to the bond enthalpies. We talked about these bond energies when we were doing, well, it was on the last exam, but we talked about it when we were dealing with Lewis structures and stuff of that nature. We found out that a triple bond is stronger than a double bond, and a double bond is stronger than a single bond. We found out that a carbon-chlorine bond would be stronger because chlorine is smaller than a carbon-bromine bond. So we've actually already talked about bond energies. Now we're just combining that concept of bond energies that we've already introduced into this concept of chemical energy and using this chemical energy to determine the enthalpy of the reaction. So bond energies, you will be given a table and you would look up your individual bond energies. You will notice that these bond energies are in kilojoules per mole. Now basically this would be one of your things that you rip off of the back of the test. Is the bond energy table. So let's look at this. Now, with respect to bond energies, you can kind of think of a bond like a stick. You got to put energy in to break it. If we put energy in, every time you put energy in, it's a positive value. And when a bond is made, it's going to be the opposite in energy. And therefore, it would be a negative value. Therefore, when we're talking about these bond enthalpies, the reactant side is going to be positive and the product side is going to be negative. That's the take home. When we talk about these bond enthalpies, the reactant side is going to be positive and the product side is going to be negative. Let's look at an example. Okay. I have methane reacting with 2 water molecules to form 4 hydrogen molecules and a carbon dioxide molecule. I will be nice enough on the test, because there is a lot of math on this test, to give you the Lewis structure. But homework-wise, you may have to develop the Lewis structure. Methane is CH4, plus we have 2 water molecules going to form 4 H2 molecules plus a CO2 molecule. You got to start here, folks, because you got to list out your bonds. In this, I have 4 carbon single bond hydrogens from the methane. Each water molecule has 2 OH bonds, but you have 2 water molecules, so you've got a total of 4 OH bonds on the reactant side. On the product side, you have 4 HH bonds, and you have 2 C double bond O's. Now, looking at the bond energy table, carbon hydrogen is 414. What sign am I going to give this carbon hydrogen? Positive, because it's a reactant. OH is 464, which will also be positive because it is a reactant. HH is 436. What sign would it have? Negative, because it's the products. And carbon dioxide, C double bond O, is 736. And again, it will be negative because it's a product. So we have 4 times 414, which is 1,656. We have 4 times 464, which is 1,856, for a total on the reactant side of 3,512. And again, that is a positive value. On the product side, we have 4 times 436, which is, and it's a negative 436, so it's a negative 1,744. And we have 2 times a negative 736, so that is a negative 1,472. Add those together, and you get a negative 3,216. So a positive 3,512 minus 3,216 means that the enthalpy for this reaction is a positive 296 kilojoules. Therefore, this reaction is endothermic, meaning energy has to drive this process, and therefore heat is a reactant. We know this information because of the sign of our enthalpy of reaction. Questions? Okay, let's look at one more example. Here we have methanol reacting with oxygen to form carbon dioxide and water. Methanol has this structure, and there are 2 of them. Plus we have 3 oxygens. Oxygen is a double bond. That's going to form 2 carbon dioxides plus 4 waters. On the reactant side, looking at the structure of methanol, you have 3 CH bonds, but there are 2 methanols. So you have a total of 6 CH bonds. You have a carbon-oxygen bond in the methanol, but there are 2 of them. So therefore you have 2 carbon single bond oxygens. And you have an OH bond in the methanol, and therefore you have 2 OH. Now, one thing that this is a great time to bring in highlighters so that you make sure you cover all of your bonds. So if I were doing this, when I was first starting, I would go, okay, 1, 2, 3. And I would write, okay, there's 2 of those, so that's 6. Then I have the CO bond, so that I would make sure, basically what I'm trying to get at is I want to make sure that I don't forget a bond. Then I would have 3 O double bond O's. That's all on the reactant side. On the product side, I have carbon dioxide, which has 2 C double bond O's, but I have 2 of them, so that's 4 C double bond O's. And I have 4 water molecules. Each water molecule has 2 OHs, so that's a total of 8 OH bonds. What sign is the enthalpy going to have on the reactant side? Positive. So this would be times a positive CH. 414. The carbon single bond oxygen is a positive 360. The OH bond is a positive 464. And the O double bond O is a positive 498. What's the sign of the ones on the product side? Negative. So we would have a negative C double bond O of 736 and a negative OH, which is going to be a negative 464. Now that I've recorded all this, I would do the math. 2,484, 720, 928, 1,494, meaning that the reactants add up to be 5,626. The products when I add those up, we get, I did it wrong. A negative 6,656. So plugging this in, 5,626 minus 6,656 is going to be a negative 1,030 kilojoules. This process is exothermic, meaning that this reaction is favorable, so it's going to go once it gets started, and therefore heat is a product. If I ask you for the information about it, you would have to identify it. I'm doing this so that you get used to writing endothermic, exothermic, and understanding what it means. Questions? Bond enthalpies are actually, to me, easier than Hess's law. But if you're not careful, you'll miss a bond. If you're not careful, you'll forget to multiply by a coefficient. So you do have to be conscientious while you're doing this process, and that's why I say this is a great time for highlighters. That way you can highlight every bond you do, and when you've multiplied it by 2, you can highlight that, so that you can make sure that you don't have an error. questions? So where have we been and where are we going this week? Yesterday, I introduced the concept of energy and the different types of energy and where you find energy in a chemical reaction. We also talked about the fact that the reaction, when you're given an energy or an enthalpy for that reaction, it is a stoichiometric value. Meaning that this negative 1030 is for 2 methanol reacting with oxygen, 3 oxygens. It is a stoichiometric value. We talked about the fact that energy is heat plus work, but relatively speaking, heat is the predominant factor. That's why we spend the most time on heat. Because in a constant volume system, heat is equal to the energy. In a constant pressure system, heat is equal to the enthalpy. So heat is the predominant leading factor. The only time work really comes into play is when you're dealing with a lot of gases, and then it's pressure volume work. This led to calorimetry. Calorimetry is how you actually determine the energy associated with a reaction. How do you do it experimentally? You go into the lab and you do calorimetry. That's how you determine these enthalpies experimentally. But we don't want to just jump into the laboratory. That can be dangerous, to just jump into a lab without knowing what to expect or what to predict. So we have a variety of ways of predicting what we may encounter. One of those is Hess's law. We can take a series of chemical reactions and we can add them up to determine the enthalpy we can expect for a target reaction. We can use bond energies. Bond energies allow us to estimate the energy associated with a chemical reaction. And the third way that we can determine the enthalpy of a reaction that we will discuss on Thursday is by using enthalpies of formation. So there's lots of ways that we determine enthalpy. The Hess's law, the bond energies, the enthalpy of formation, that's going to give us a pretty good idea of the energy associated with the chemical reaction before we just jump into the laboratory and do the calorimetry. So we can be safe when we're doing those reactions. Any questions? I did upload a version of the lab. Unfortunately, my 8 a.m. I did not record, and my 2 p.m. my iPad was dying too bad. So the 11 o'clock is the lab that got uploaded because it was the only one that was remotely viable. With that, I will let you go for today.